Hello and welcome to this video on the gas laws. So we're leading up, I'm using Chemistry, the Central Science by Brown, LeMay, Bursten, and Murphy. But of course, any chemistry textbook will deal with the gas laws. We're building up to the next video, which is on the ideal gas law, PV equals nRT. But in this video, we deal with some of the kind of partial gas laws that led up to that, which is fun if you like the history of science, because we dig back into some of the earliest movements in chemistry. So, for example, Robert Boyle came up with Boyle's law in the 1600s with the rise of modern science. Why did science suddenly begin to grow in the 15 and 1600s? That's a great question and not what this video is on. So I'm going to keep moving. What are the four variables? Well, we've basically over the period of a couple hundred years, four variables became clear in the equation metaphorically and literally, of how gases work. These variables are the volume, and this was one thing that was easily observed because you could see that things expanded or contracted. Pressure. Remember in a previous video, actually the previous video to this one, we talked about Torricelli and Pascal and how they argued in the 1600s that the higher you went up a volcano, the less atmospheric pressure there was. Temperature. How that when temperature increases, the volume increases, those sorts of things. And then there's basically the amount of gas, how much gas is actually present. These are the four variables that it became clear were involved in the behavior, the physical properties of gas. And that gases, even though there might be different gases, as it would be eventually clear, they all behave very similarly with regard to their physical characteristics. So the first of these relationships to be explored is a relationship between volume and pressure. And of course, this makes perfect sense to us, that you put pressure on a gas, its volume is going to decrease. If the pressure decreases, the volume increases. So a helium balloon, the farther it goes up in the atmosphere, where there's less pressure, expands. Yay, what a complicated idea. So Robert Boyle, kind of came up with this in the 1600s. We call it Boyle's law. And basically it's the idea that volume and pressure are inversely proportional. That as one goes up, the other goes down, and as the other goes up, the other one goes down. Or you might say that at a constant temperature, so if we keep the temperature constant, the volume is equal to 1 over the pressure times some constant. This is the thing in equations, is that when something is directly proportional, then all you need to do is add a constant of some kind to one or the other side, and it becomes an equation. It becomes equal. Proportionate means they both, they go up at the same basic rate or go down at the same basic rate. So all you have to do is find out what the constant is, and often this was done experimentally, then ding, you've got an actual equation where the quantities are equal. If you graph volume, and in Chemistry, the Central Science, there is what's called a PV diagram of this, that if you diagram volume versus 1 over the pressure, it's a line. It's a linear relationship. That's what we mean by saying something is directly or indirectly or directly or inversely proportional, is that if you graph those two against each other, or if they're inversely proportional, if you graph it with the inverse, like these, you get a line. If you graph volume and pressure to each other, you get a kind of a curve on a PV diagram, pressure volume diagram. Well, okay. Another way of saying this is that if you multiply P times V, you get a constant. So using a little algebra, if you multiply both sides by p, this becomes 1, and this side becomes PV. So PV equals 1 times a constant. Therefore, PV equals a constant. So this is Boyle's law, that volume and pressure are inversely proportional, which means that PV times each other equals a constant. Okay, so that was the beginnings of gas laws with Robert Boyle in the 1600s. So the second relationship in the 1700s to be explored by Charles was his last name. I'm forgetting at the moment what his first name was, but Charles explored the relationship between temperature and volume. And at the very beginning, I expressed this, that as you increase the temperature, the volume expands. As you decrease the temperature, the volume decreases. We see this on highways with solids, for example, where they now have this gap in the winter. There is a kind of even with concrete, because as it becomes hotter, the concrete expands. And so they put a little gap in the highways so that in the summer it can expand to where it closes. And then in the winter it pulls apart a little bit. So as things are heated up, they expand. As things are cooled down, they contract. And so another way of saying this is that volume and temperature are directly proportional. As temperature goes up, volume goes up. As temperature goes down, volume goes down. And this, especially with gases, it's more noticeable. And so if we keep the pressure constant, then volume equals temperature times some constant. They're directly proportional. And so all we have to do is find out experimentally what the constant is, and we've got an equation. Or another way of putting this is that if you divide velocity by temperature or vice versa, you get a constant. By the way, let me just not assume you know what a constant is. A constant is a number that is constant. It's a number that doesn't change. So it's basically a number. Okay, sorry, I should have said that at the beginning. I don't know how much math you've had. I assume if you're at this stage of a chemistry course, you've had some math. Okay, so now interesting, Charles, was it Charles that charted this? But if you chart this, so again, if you put volume and temperature on a chart, you get a diagonal line. And if you take that line backwards, what you find on the chart is that when volume goes to 0, the temperature goes to negative 273 degrees. And so this became known as absolute zero, the zero beyond which one cannot go. Of course, you can't really get that far. You can't get all the way to absolute zero. But there was a guy, his name was actually Thomson, but as it is, he was his lordly title as a British guy was Lord Kelvin. And Lord Kelvin is the one who proposed a different temperature scale. So in science, we tend to use the Celsius scale. The Kelvin scale is simply the Celsius scale beginning at 0, at absolute 0. So negative 273 degrees, I think it's 0.14 or something like that. Negative 273 degrees is 0 on the Kelvin scale, and then it goes up by Celsius units. And so 0 degrees Celsius is 270 degrees Kelvin, if that makes sense. And I think we've said this at the very beginning of this series of videos and at the beginning of the chemistry book. Okay, so the last variable was explored by Avogadro, I believe, in the 1800s. And that has to do with the quantity of molecules. Another way of calling this is Guy-Lussac's law, I believe. So other textbooks will use that nomenclature. He was French. So volume and the amount of moles are directly proportional. So if you put more gas molecules into a space, the volume will expand. They go up. So as the number of molecules goes up, the volume goes up. And so if you have a constant temperature and pressure, the volume is going to equal the number of, let's say, moles, the number of moles of gas times a constant. Okay, here's Avogadro's hypothesis, by the way. This is, we all know Avogadro's number. That's the number of molecules in a mole, the number of molecules in 12 grams of carbon-12, 6 times 10 to the 23rd molecules, for example. We know Avogadro's law here, or Guy-Lussac's law, that volume and the number of moles are proportionate. So now we have Avogadro's hypothesis, and that is that if you have equal volumes of gases at the same temperature and pressure, you will have the same number of molecules. That's quite interesting. So whether you're talking about hydrogen or oxygen or nitrogen or whatever gas you're talking about, that if those two gases are at the same temperature and pressure, and they have an equal volume, then they will have an equal number of molecules. So we're all set up now for the ideal gas equation, which we will do in the next video if I survive until tomorrow or today. I don't know when I'll do it, actually. So have a great day, and may you not Boyle, Charles, or Avogadro today. So have a good day.